In today's video, we're going to learn about the Bohr model of the atom and the advancement of our quantum mechanical theory as it applies to all matter in the world. So let's take a step back first. Let's go back to the old days when we had Dalton's laws and that was about it. Dalton came up with the billiard ball model of the atom, which basically was a homogeneous sphere of uniformity. And if that's really how atoms were, now advancing with our ability to use light to analyze matter, basically every single thing would reflect off of it. This is clearly not the current model of the atom, and it's not accurate. But it was a good step in the right direction. After the billiard ball model, we had the plum pudding model of the atom, after Thomson's cathode ray tube experiments, where he determined that there was an electron in the atom, but there wasn't really any specificity to any other regions of the atom. They didn't know about the nucleus. They thought of it as a ball of positive sphere with an electron floating about. Then Ernest Rutherford said, well, he came up with the planetary model, or the classical solar system model of the atom, but there were problems with that. Like, everything would collapse on itself, because you have a negatively charged thing orbiting a positively charged thing. Eventually they were going to meet and result in kaboom. So clearly that didn't happen, so people kept looking into what actually did happen. And then we got to the Bohr model of the atom. And Bohr looked at the ability of hydrogen atoms, and he used other atoms as well, but focused primarily on the hydrogen atom to look at what happened when hydrogen molecules were heated and then what light they gave off. So hydrogen, this is a model of it, where you just have a single proton and a single electron. He viewed it as having discrete energy levels, and this was really the beginning of quantum revolution, where it came up with the idea that the energy from the electron was gained or lost in discrete chunks of energy called quanta. So you can see here, and I'm actually going to slow it down now, as the electron, right now it's orbiting at a higher energy level, but we'll let it fall back down. You can just keep following. Now it's at its ground state. When it gets struck, this is probably going to do it. I think it's going to do it. Yes, it absorbed that energy and jumped up to an excited state. Then as it falls back down, it doesn't necessarily have to be to the ground state. It releases that energy in the form of the photon. And basically what he described as the difference between the energy levels that the electron's jumping to and from is going to be equal to the energy of the photon that it is emitting. So different drops, if you will release different amounts of energy. The further the drop, the more energy it's going to lose. And you notice that it's not really gradually climbing from the inner shell to an outer shell. It is basically teleporting. And that's because it's not gaining energy gradually, getting pushed up a hill where it needs a constant force being applied. It is immediate. It gains the energy. Let's see it happen. Boop. It gains the energy at once, and then it releases the energy at once. Now, it doesn't have to fall all the way back down like it did there, but there are a bunch of different transitions it undergoes, some of which we see and some of which we do not. And we actually have an equation now using a modification of the Rydberg constant to allow us to calculate the energy change observed with these electronic transitions. So the change in energy is equal to this modified version of the Rydberg constant times 1 over your final energy level, n represents the energy level, minus 1 over the initial energy level, both of those squared. So we could calculate the energy change observed as an electron falls from the 4th energy level to the 2nd. And all we have to do is plug that in. So you have this, 1 over 2 squared, which is 1 over 4, 1 over 4 squared, which is 1 over 16. When you execute that function, you get negative 4.08 times 10 to the negative 19th joules. So that's the amount of energy lost by the electron within the atom, and that is equal to the amount of energy possessed by the photon that is ejected. So if we were going to determine the wavelength of the photon emitted as that happened, what we can do is we can modify our energy and wavelength relationship to this, and then all we have to do is plug in Planck's constant, plug in the speed of light, and then plug in the energy change we observed. Keeping in mind that this is going to have a positive value because the energy lost by the atom is equal to the energy gained by the, or not energy gained, but the energy possessed by the photon, and we would find that that is 487 nanometers. And if we look over here, we can actually see that that transition of going from the fourth energy level, dropping down to the second, would release this color of light, 487 nanometers. And if I let this run for a little while, I'm just going to have to go faster, you can see that there's all sorts of transitions that occur. There's only really these several in the visible region, and you have a lot more that are in the ultraviolet region. These would have to do with energy transitions of large scale, typically dropping down to the first energy level, and then you have also some smaller transitions where, like, if it dropped from the sixth energy level to the fifth, not as much energy associated, and when you plug it into the equation, you'll get a smaller value for energy, and therefore a larger value for wavelength. So this is the Bohr model of the atom, where we look at electrons, and I'll slow it down now that we've collected some data. You can see there's also that violet wavelength that I knew would be there. That's the Bohr model. After the Bohr model, got a little bit more specific. Someone named de Broglie came along and said that, you know, all matter has wave-like properties, not just light. And he came up with the de Broglie model of the atom, where the electrons exist as wave functions within the atom. We're not going to do too much with this, but this is a little bit more accurate. And then Erwin Schrödinger came along and basically said, it's not quite just wave functions, it's based off of probabilities of wave functions where we could find the electrons in an atom, and that's where they could get excited to or drop down. One important thing to point out about the Bohr model is it really only works, the Bohr model is good, but the calculations using that equation only really work when we're talking about hydrogen atoms. Things get a lot more complicated when you add an additional proton, some neutrons, and then you have interference between other electrons. It just gets messy, so we'll stick with this.